binary search and a fake coin problem. In this part, we will learn two topics. The first one, binary search, and the second one, fake coin problem. B.1, binary search, elimination. We will use the elimination method to solve the binary search problem. All right. Our problem number 13, search an ordered array. You can see the meaning from the title. Given an ordered array. So this time, our data has this special property, ordered. That is very important. That's the array. And a search key V. The question, how to find an index I, array index I, such that V equals A of I. That simple. Okay, So this is the problem I think many of you are very familiar with. Even the binary search, I believe most of you are already quite familiar with it. But we have a lot of things to learn. Okay? So this part, we have a lot of things to learn. All right, so let's start. Let's do some analysis. Let's think about what kind of method we want to use for this problem. We want to learn some general problem-solving method, strategy. So you can say, anyway, All right, the idea. For this situation, the idea we want to use, reduce the problem size by the ordered data property. The ordered data, this property is very nice. We should take advantage of it. Here, we do not need to do anything. We are given ordered data. So that is a very important information. Remember, when we solve, so we have one problem we solved before called element uniqueness problem. In that problem, we are given unordered array, and our method, we sort it first. The cost is pretty high. We sort it, the cost is n log n. Let me use the asymptotic notation, big O of n log n. That's a lot of cost. Okay? But here we don't need to pay anything. We already have that order data property. So definitely we need to use it. All right, so then the method. In this problem, I want to talk about a very useful method called elimination method. Elimination method. From its name, you can guess what we should do. Do elimination. Given some conditions, if we can find some insight from the given conditions, we can use those conditions to eliminate as many elements as possible. If you can do that effectively, then you will reduce the problem size quickly. That's the basic idea of this elimination method. Very useful. Here, we just, view it from high level, very abstract. After you have more experience, later, I will give you several examples, several questions. If you can use elimination method to reduce the problem size, then you can solve it. effectively. Yeah. All right. Yeah. So let's continue. Yeah. How can we take advantage of the ordered data property? Yeah. So we need to visualize the procedure. Yeah. We don't want to, do abstract thinking here. We need something very concrete, very specific to build up some experience here. Yeah. All right. Now, let me draw a diagram. So we try to get some, good visualization on this problem. We want to explore the ordering property. Yeah. Here, let us assume the array is sorted in ascending order. Okay? And we are given a key V here. Now, we can do comparison. We do comparison by comparison to reduce the problem size. Okay? So that's the thing we need to do. All right. We can do when we do comparison, we have a lot of freedom to choose which element to compare with, right? So the last element, the element somewhere in the middle, the first element, you can choose, many different ways. But the question is, which one is the best choice? That's the question. We want to know the answer. Okay? Yeah. So more specifically, the question we ask this way: after one comparison, how many elements can be eliminated? So here you can see we use this word, eliminated. That's related to the elimination method. Yeah. So we want to connect it to the elimination method. Okay. How many elements? Yeah. So we want to eliminate as many as possible. That's our goal. Okay. All right. Yeah. So now we try to answer this question. Yeah. All right. First, let's do some experiment. The first experiment, we compare V with the last element. Yeah. One experiment. We need some experience. Okay. When we do this comparison, you can see there are two cases. Okay. The first case, V greater than or equal to A sub n minus 1, and we can get the answer immediately. So that's why I say it is the best case, because we get the problem solved already. Yeah, right? When V greater or equal to A sub n minus 1, the problem is solved. One comparison. So that's the best case. But most of the time you cannot expect that best case. Most of the time we need to consider other cases when V less than A sub n minus 1. Okay? Yeah, because this situation happens more frequently than the lucky case, best case. Okay? The probability will be much higher for this unlucky case. Yeah, let me just call unlucky case. Much higher the probability than the lucky case. Okay? Yeah. But if you get into this part, how many elements can you eliminate after one comparison? Only one, right? Only you just eliminate the last element. All the remaining other elements you need to consider. That's not a good problem reduction, right? Problem size reduction. The problem size only reduced by 1. Not very efficient. Okay? So you can see, that means this choice is not a good choice, right? Yeah. So here, so you can see we should not focus on the best case. We should focus on the worst case. Yeah. So another thing related to this phenomenon, Murphy's Law, right? People talk about this Murphy's Law. So that's something related to the worst case. Yeah. So what's that? Yeah, here. And it means anything that can go wrong will go wrong. Anything that can go wrong, so that's the worst case. Something really bad could happen, will go wrong. Or we will say we're likely to go wrong precisely, but based on many people's experience in real life, they feel they have the worst case. So based on their psychology, they get impression. The same as describe it as the Murphy's Law. Okay, by the psychology, people's psychology, they get this experience like this. Okay, yeah, it's not a scientific law. Okay, yeah, Murphy's Law is not a scientific law. Yeah, something reflected by people's impression. Okay, yeah, here I just use this real life experience to give you the idea. We should focus on the worst case. All right, yeah. So now, the question. Now, how do we eliminate as many elements as possible? Our goal, as many as possible. Now we need to talk about our strategy in this situation. The strategy, yeah. Here, now, I remember I mentioned this principle once before. Yeah. So here, let's just use it another time. Yeah. Balancing principle. Balancing principle. So what's that? So when we make a decision like this, many times we need to make decision. Okay? When we make decision, we have many different choices. Okay? Which choice is usually the best based on the balancing principle? The most balanced choice is the best. The most balanced choice is usually the best of the principle. Okay? Principle just something, likely to give you a good solution, but still it's not a scientific law, right? It's not a scientific law, so you cannot prove it. Yeah. So that's people summarize from the real world experience. You should follow. If you follow this principle, you are very likely you can get a good result. So that's the meaning of principle. Okay, yeah. So here, the balancing principle. When we make our decision, compare which element to compare, the one in the middle, because in that way you split the file into two subfiles. The two subfiles are quite balanced. The size difference of the two subfiles is the smallest. That means the most balanced decision. Okay? Yeah. So now, based on that, we compare the one right in the middle. The element position should be close to the midpoint as possible, as close to the midpoint as possible. So we call it a median. Yeah. So that's the definition of the median. In a sorted array, the element in the middle position, the median. Okay? Yeah. So then some students at this point may ask me this question. When you have even number of elements, n equals even number of elements, what is the median? Right? What is the median? Yeah. For odd number, we know the element in the middle, we know that. But with even number of elements, what element is really the one in the middle? Here, let me just draw 4 elements. in this example, which element is the so-called median. Yeah. Here, let me give you the definition in computer science, not in math, not in arithmetic, in grade schools. In grade schools, the definition could be different. Okay, I saw that definition before. It's different from our definition. Okay, our definition is this. Okay, all right. Look at these two elements in the middle, right? So they have the similar position. Okay, yeah, they're close to the absolute midpoint is here. They are equally close to the absolute midpoint. Okay, yeah. So we call this one, we call the left median. Okay, it is also median, but left median. All right, this one, right median. Okay, two medians. Left median and the right median, two medians. All right, but many times we only use one median. Right? Yeah, most of the time we only use one median. When we say median in computer science, the definition we mean the left median. Okay, if we do not say left or right by default, we refer to left median. That's the median. Okay, so now its meaning is clear. Okay, although if you use the right median, you get same performance. Same performance. Yeah, so that's fine. Yeah. All right. So with this clarification, so let's go to the next step. Let's go back to the elimination method here. Okay. All right. Now we have the observation, with respect to that elimination consideration. So what's that? Every time when we do one comparison, if we compare it with the median, we can throw away almost 1/2 of the elements. Almost. Slightly different. The difference could be one difference. Yeah. Yeah. So nearly half of the problem size, data size reduced. But we can say, because computer science, we frequently use approximation, right? Yeah, it is very natural to use approximation. So if we use the approximation, it's a pretty good approximation. So we say we cut the problem size by half. Good enough. Very good approximation. We should be very satisfied. Okay, yeah. So that's what we can get from our part B.1. This observation, this, analysis. Yeah. Part B.2, so we will solve it and actually solve it is almost there with this observation to find a solution, almost there, but we need to do analysis of the efficiency in our part B.2. All right, so let me stop here. Yeah.